Hello, Muhammad Alif Aiman here, back again to talk about my experiment. This experiment is all about diodes. So, what are they? Diodes are made out of semiconductors, namely two types, N-type and P-type. They both combine to make a diode, and the part where they're combined is called a PN junction, or a depletion layer. Depending on the bias of the diode, as in how they are connected to respective to a battery, current can either flow through or be blocked by them. Diodes come in many forms. Now, our objective today is to investigate the basic characteristics of a diode, Zener diode, a light emitting diode, or mostly known as an LED, and to see how they are normally applied to electronic circuits. So, let's get started. Part 1 shows the basic function of a diode. As I cited earlier in the intro, the diode will work depending on how it's connected with respect to the power source. In A, it is connected in forward bias, while in B, it is in reverse bias. When in forward bias, the depletion layer tends to make there to be less resistance, allowing current to flow. Whilst in reverse bias, it thickens, increasing the resistance, making the current hard to pass through it, as in, the current will be blocked by the diode. Now, we've discussed about regular diodes. It's time to talk about Zener diodes. They basically have the same working principle, but a Zener diode works best when in reverse bias. The data shown now will support it. See how after the 10 volt, the voltage only increases bit by bit. This means that the output voltage is regulated. Usually a circuit like this is called a voltage regulator. They're perfect for components that have specific conditions to work at maximum efficiency. Okay, everyone likes Christmas lights and riot decorations, right? They're colorful, right? Well, they are made out of LEDs. LEDs come in many colors, as can be seen from the application of it. The working principle is that they must be supplied a specific amount of power to pass through the diode's forward voltage, which will activate them. Here, we investigate how much it is. After experimenting, the amount of voltage required for both yellow and red LEDs is 1.615 volts, though that doesn't seem to be right, as different colors should have different wavelengths. It seems that the LEDs in EZEDA had problems, and I say investigating this part of the experiment was not successful. Now that we talked about three diodes, let's see how a normal diode is applied to a circuit and the result when it's paired with other components. When a capacitor is paired with a diode, the circuit becomes a clamper circuit. This means the output voltage will either shift up in the positive or shift down depending on the orientation of the diode. If it's orientated like this, the output waveform would be like this. This is called a positive clamper, and if it's reversed, it will be a negative clamper. In the positive clamper, in the first half cycle of the circuit, the diode will be in forward bias, which will make the capacitor to charge up. But in the second half cycle, the diode will be now in reverse bias, and the capacitor will be discharging, as now the circuit is not complete, which will not make the capacitor active. Usually, voltage clampers are used to remove distortion. When the circuit is built like the network right now, the output waveform will have its amplitude shrunk. This is called a voltage clipper circuit. This happens due to the resistor absorbing some of the current, which shrinks the output. The output amplitude is affected by the magnitude of resistance. Also, one thing to note, the output is in the same shape as the input waveform. It's because there are two diodes present. Voltage clippers are usually used for the separation of synchronization signals from the composite picture signals. Diodes can also be used for rectification. Let's compare these two waveforms. As we can see, one of the waveforms has the amplitude above the 0 volt line, while the other only has it below the 0 volt line. This is called half-wave rectification. Only half of the input waveform is sent to the load. I think the working theory is pretty obvious if you paid attention so far. But since a diode only allows current through if it's in forward bias, in the first half cycle, the current is passing through, whilst in the next half cycle, it is not. This is why there is no voltage below 0 volts, as in the second half cycle, current is not passed through to the load. The case is reversed for the negative half-wave rectification. Usually, this circuit is used to change AC sources into DC sources. Finally, a diode works in conjunction with capacitors and resistors in this network form to make a voltage doubler circuit. In the first half cycle, capacitor C2 is charged because diode D7 is in forward bias, while D5 is in reverse, making C3 inactive. Charges are stored in C2 up to the peak voltage during the cycle. When the next half cycle starts, the operation is reversed, meaning D5 is forward bias instead of D7, and C3 is charging while C2 discharges, but C3 charges to double the value due to C2 already being at peak voltage. Since C2 discharged, the voltage released is added to the waveform produced at the load, which results in the waveform being rippled as capacitor C3 discharges and is being ready for the next half cycle. The trend of the doubler is that the multiplied circuit will go down when the resistor has a low resistance value, as can be seen from all of these graphs shown now. So, what is the application of this? Well, the doubler is from a family of voltage multipliers. Usually, voltage multipliers are an expensive way to increase voltage, which is useful for components which require more power other than from other components. Uses are in copiers, CRTs, laser pointers, stuff that requires high power. Now, we have come to the end of this video. If you have been paying attention, you can see that diodes are very versatile components and come in many archetypes. Also, as I stated earlier in the LED part, this experiment was done in a simulation program called EasyEDA. Real diodes would behave very differently, and they would be affected by the temperature of the room and other variables. Thank you for watching this video. Until we meet again for the next video. Goodbye.